Hi everyone. So we will start today's lecture. So as you know, we have posted our homework 1. So please check the file and start working on the homework as early as possible. And if you have any question, please contact TA or ask me during the office hours or send me email to arrange some time to discuss. Okay. So basically, so before we start today's lecture, let me remind you that I'm trying very hard to keep my note online. So in case you don't know, the lecture note will be basically updated in a not so regular pattern, but basically I'll try to type in everything that we have discussed during the time of the lecture. However, as I mentioned at the Google Classroom, some part of the lecture note is not yet finished, but you can still try to read those parts that is already there and try to keep up with the content of the lecture note. Okay, and also the update not only includes the lecture notes, it also includes some of the important reference. For example, in the introduction section, you'll see there are some additional reference. For example, like this one, it is related to some of the interesting papers that you can check online about, what are some of the examples about for example, emergent phenomena and statistical physics. And there are some more like a general introduction about related ideas. In this case, it is related to constructing a model to understand the results of the elections of US president and things like that. And also, I hope that at least the course is not a course that try to limit your possibility. The hope for this course is try to broaden your possibility to connect to various different research area. So in principle, if you feel like the lecture is kind of boring and you want to learn more about a more advanced subject, I encourage you to do so by Google. And here are some of the very interesting things I found online. For example, like machine learning, there's a very nice reference, and my web's connection is a little bit slow, but it still works. So here is the archive system. If you do research, you probably will know this system. It basically just is like the most updated research papers that is not yet published on journals, but you can still, through this system, you can find what they are working on. For example, this one is a very long, maybe some kind of book or something that basically discuss the principles of deep learning theory. At the very beginning, you'll think that how it is related to statistical mechanics. It seems like it is not so obvious. But once you click the PDF file, there's a PDF here. So once you click it, it will download it, and it's 400 something pages, so it will take a little bit while. So so you'll see a lot of the content that we have discussed in the first few lectures are basically some very simple ideas about that has its value for the research topics. For example, why it takes so long? For example, in the first few lectures, we discussed the random walks, and one of the important ideas is about the effective theory. And we go from the microscopic theory to the macroscopic theory, which is the diffusion equation. So in this terminology, the diffusion equation is the effective theory for the microscopic model. Okay, so this kind of concept actually is widely used in various different areas, including the deep learning theory. I'm just waiting. Now it is the content of this particular document. So you'll see at the initial discussion, they discuss what is the effective theory. And then later on, they talk about Gaussian integrals, which is something that we have done in the homeworks, and that tells you that why it is so important and also probability and correlations and statistics. That's all the subject that we are going to cover in this course. So this course is not going to be, just a useless pedagogical course. It is actually quite useful. And if you want to learn more about statistics, for example, in the next semester or at the end of the semester, we might cover something called renormalization group. And you can also see that there's a whole chapter discussing about the picture of renormalization group and other things that is related to machine learning. So this is just one subject where you can see that, statistical mechanics is quite important to understand some of the concept in, it's gone. Okay, I'll just take it. Some of the concept related to deep learning, okay? And also, I want to mention that in addition to those, there are also some very interesting articles that I put it in the links. For example, one of the very interesting things about the simulated annealing. It is something related to the Nobel Prize of last year, the spin glass problem. You might feel like why we want to understand spin glass, because actually at the very beginning, it is a subject related to how to understand some spatial property in the materials. However, it turns out that when people study it, basically we open a can of worms that there are a bunch of new physics there. And one of the discovery people found is that actually you can use a very interesting idea, which is basically you can try to optimize your problem through the concept of related to partition function, which we will also talk about in this semester. And this method is called simulated annealing. And there are some very, this is basically the original idea. Now you can check this paper and see how the idea came out. And you'll see a lot of notation that you are familiar with, like entropy, temperature, partition function, free energy, and correlation functions, and things like that. So if you feel like, at the very beginning, the pace of the course is a little bit slow for you, and you want to, get something that's more challenging or more closer to the research frontier, please try to take a look about the possible material I found online, and also something related to black holes, in case some of you are working on high energy and still want to find some connections about statistical mechanics and the black holes. Okay, so that's one part. And the other part is that at this, at this new generation, it is almost impossible to do research without knowing some of the computation technique. So on this website, I also include two simple sections is related to a basic introduction about the Python and how to use Python as your numerical tool to help you do research or finish your homework. So this two Jupyter notebook is basically the lecture notes provided by Professor Chris Lauman, who is at Boston University. I got this lecture notes when I was in the ICTP, is an institute in Italy. And where's the link? Here it is. So you can check the YouTube channel about this school if you are interested in more research-oriented subject related to modern condensed matter physics. But the point of mentioning that is that these two materials give you the enough background to help you to get going, to use Python to plot something or doing some numerical calculations. And here are some introduction about how to do that, and also some very simple exercise that how to, just do some very simple numerics and write some programs. It should be quite self-explanatory. And also, these two notebooks are basically written in Jupyter. So in order to run Jupyter, you can just go to this package where I also included, is that you can try to install this Anaconda package. And so Anaconda is running, but it's a bit slow. You can just download this thing and install it on your laptop or desktop. Then once you finish download it, then you should be able to have this kind of package for scientific computation. You can just click, a Jupyter Notebook, then something will pop up in your browser. And let's see, I think I put it in test. So basically, oh, by the way, I forgot. Basically, you can use new to open a new Python Jupyter. Are there problems? No. Okay, good. Then you should be able to, do some very simple calculations, something like this, and you press Shift and Enter, and then you can ask what's x plus 1, and it tells you it's 2. Okay, so that's like some very simple starting points for you to get Python to work. And so please take a look if, for example, when you're doing the homework, you don't know how to plot things, or maybe you need Mathematica or MATLAB. If you're familiar with those, that's fine, but Python is a free software. So if you don't have both of them, you can just use Python to plot or do numerics. Okay, so that's something that's added to our website. And I think that's what I want to say for now. Then are there any questions so far? Okay, if not, I will stop sharing. So we will start by review what we have done in the last few lectures, and sorry for keep you waiting. Okay, so the first thing is that we try to solve the Green's function. Of the diffusion equation. Okay, and basically the Green's function satisfies this particular relation. And in our last lecture, we basically can derive the Green's function as a function that has this Gaussian form. And in our homework, we basically have a Fourier transform of a Gaussian function. And I asked you to do the contour integral and things like that. And some of you feel confused. Either it's just a result, it's just a simple Gaussian integral. And the answer is, the final answer is yes. But the problem is that what we are doing is actually integration in the complex plan. So in principle, I want you to do the complex integral honestly, and you need to understand like how to perform this integral in the homework. Okay, but anyway, this is the Green's function for the diffusion equation that we have derived in the last lecture. And then we also go through some of the basic definition for the statistics. And also, we learned some very simple mathematics about the Gaussian integral, which is exact, and also the saddle point approximation. Which is a very general method to approximate integral when there are some saddle point structure. And we use Stirling's approximation as an example to show that how this method works. Okay, and the most important results that we derived is basically the relative standard deviation for a random for a sequence of random variables. Basically is defined by this quantity, and you will be proportional with the inverse of square root of n. Okay, and what does that mean? It tells us that when the degrees of freedom or the number of random variables is large, then the fluctuation and the mean value are related with each other through this square root, inverse of square root of n. And when the degrees of freedom is large, that means the fluctuation is tiny compared with the mean value. And that will give you a figure that looks like this, that you will have a mean value as n here. And the system will just fluctuate tiny on top of that mean value, but it will be strongly suppressed by this inverse of square root of n, okay? So in the last lecture, we mentioned that this is a really important result because it tells us that it is possible that a regularity of the physics observable could happen when n is large. And then we also try to motivate a little bit about the fact that we are starting from some deterministic description at the microscopic level. And then we want to change that deterministic description into a statistical description. And the motivation for that is because we start from the microscopic world. Basically, we have tons of degrees of freedom that it is impossible for us to keep track of them. So instead of doing the deterministic description, we want to use statistics to describe the system as a whole. So today we are going to elaborate more on this second point, because in the last few lectures, basically we are focusing on the first point. And the way we elaborate on this second point is the strategy is like that. We start from a simple example. Basically the ideal gas model. And I hope that I can use this simple example to demonstrate how a statistical description can actually help us to understand the ideal gas model. And then using this simple model, we want to generalize this idea into a more general framework. That's basically the spirit of the statistical mechanics. And the key important or the key object that we that can help us to make this generalization is the idea of entropy. Okay, so entropy is a concept that basically is defined from thermodynamics. Okay, so basically we want to have a very quick review about thermodynamics. And try to focus on what is the role of entropy in the whole framework of thermodynamics. So basically, we will formulate thermodynamics by defining the function of entropy. Okay. And in order to do that, we need to have some basic description about our thermodynamic system. So there are some important concepts, for example, extensive and intensive variables. And also, I will introduce the central problem of thermodynamics. basically it's asking what type of question are we trying to ask in thermodynamics. And then we'll found that actually entropy is basically postulated to be the solution for this central problem of thermodynamics. Okay, and then one of the important idea I need to talk about is the gender transformation. Okay, so this part of the lecture will basically be a super short course about reviewing thermodynamics. Okay, so I'll just post the key ideas and point out the key structure, but I'm not going to elaborate everything, because importantly that's supposed to be some of the course that is already been taught in undergrad studies. So I'll just try to take another route. Instead of talking about all the details, I'll take the approach that once we are able to define what is entropy, there's actually a framework that you can understand the whole thermodynamics by analyzing this function of entropy as a function of extensive variables. And why do we want to talk about entropy? Because the key ingredient to move from deterministic description to statistical description is to build a connection of the entropy function with the microscopic physics. So the key is actually the microscopic interpretation or the microscopic picture of entropy. And that will lead to the foundation of statistical mechanics. Okay, so that's basically the idea. We start from a simple example and try to see how statistics description works in this simple example. Then we review thermodynamics and try to build this particular, try to have the picture that entropy is actually a thermodynamic quantity that have no microscopic description under the thermodynamics framework. But in order to have the microscopic interpretation, basically what you need to rely on is the discovery of Boltzmann. Wait, I think there's no minus sign, sorry. Which connects the macroscopic thermodynamic function with this omega, which is the microscopic, which is basically the accessible phase space. Okay, so that's basically a strategy. So so now I think it is about time for us to start from the description of the ideal gas model. So are there any questions so far? Okay, if not, I'll continue. Okay. So let's start from the microscopic picture and see what kind of problem that we are trying to analyze. So suppose we have a one particle system. Okay, we know how to describe the system quite well. Basically, you need to specify the initial condition. Oh, by the way, here we assume that we are dealing with the classical system. Later in the lecture, we will talk about the quantum mechanics, but let's focus on the classical system for now. So once we know the initial condition of our particle, for example, I know what is the position of my particle, let me denote it by R1, and I know what is the velocity of my particle, let me denote it by V1, then we have learned the classical mechanics previously. We can use the equation of motion, which is derived from Newton's second law. And then once we know the acceleration and the two initial conditions, the position and the velocity, then we can predict what is the behavior for this particle. For example, we can start to do arbitrary motion, depends on what kind of force we apply on this particle. But the point is that we can know what it is going to do in the future. So now, if we try to start with this idea, but consider the m-particle system. Okay, then the initial condition will be a bit more complicated. Is that you have m position vectors and you have n velocity vectors, and you need to collect all of them in order to specify the initial condition of your system. Okay, then once you have the initial condition, you want to ask what is the equation of motion, and it turns out that at this point you will have the Newton equation again, but now you need to be careful about the system because you need to include all possible interaction between the jth particle and the reference particle, basically the ith particle that you want to analyze. So basically this is the total force, and it should be equal to mass times the acceleration of that particular reference particle. So when we write it in this way, you can notice that it's actually a very complicated coupled equations. So in order to solve that, you need to spend a lot of computation resources. So the question is, do we still want to use this method to understand our system? Or maybe we can find other description that we can try to understand our system. And actually, we can try to think from a more practical side. Suppose I have a system. Is it ever possible that I can have this type of initial condition when I runs from 1 to 10 to the power of 23? The answer is no, because usually we just don't have all the information about the position and the velocity of our particles. So we don't have that. So how to do that if we want to simplify or try to make sense of our system? And that's one thing, basically lack of information of our system. Okay. And the second challenge is that even if you are able to solve this equation of motion such that you got all the information of your system, it is still difficult to define what do you mean by understand your system. The reason is there's no way that you can check to 10 to the power of 23 variable and using these variables and saying that, I understand this 10 to the power of 23 variables will give me some specific behavior about the pressure. So usually it is not interpretable. So you are not able to understand this big data. So what statistical mechanics and trying to prevent is that, or trying to help us is that thermodynamics can be considered as a way to describe these macroscopic degrees of freedom, but only use a relatively small but finite amount of variables. And those variables are something that we are familiar with. For example, the total energy of your system, the total volume of your system, the total number of particles in your system. And use those quantities, and we try to build some relations between them. And that's the idea or like the spirit of thermodynamics. Okay. So in order to do that, like how to make this logical jump is that basically, because we don't know the full information about the initial condition of our system. So instead, we kind of try to make assumptions about our initial condition. So let me try to write down. Okay. So we hope that when we are trying to make these assumptions are, to some extent accurate enough to give us some predictions. Then we can predict some physical behavior. Okay. At this point, it's not obvious that you can do that, but let's try to use a simple illustration about what do I mean by that. So in principle, you have a initial system, and let's try to use this big set to represent all the possible initial condition. So once you make some assumption about the initial condition, what does that mean? You only consider a subset of this big set, okay? So this is like an initial condition, okay? Then we are trying to say that once we use this use those initial conditions and try to make physical predictions, they are almost true for most of the time. So what does that mean? It means that if we are able to justify, or like at least we try to believe that it is true, that the initial condition that we try to pick is general enough such that our system will most of the time will stay within this region where the initial condition that we assume to be valid. For example, if I start from some of the initial condition in here, and maybe the system will follow some deterministic description like Newton's law or something, then you will start to evolve in this space, okay? And at some point you will reach some of the parameter space that is not described by this initial condition. But we hope that we can still make statistical description using the information that we got from this particular chosen set. So how is it possible? The idea is that if the case or if the time the system will evolve into a situation that is not satisfying our assumption is measure 0, then we basically achieve our goal. That is, there are very, very low probability that our system will stay in this red region. Or like this region is very unlikely. Okay, so if we can reach that goal, then this assumption of the initial condition will be very useful. Okay, so let's start from the ideal gas model to demonstrate what do I mean by those words. Okay. So suppose we have a box And in this box, we have some particles that just move in different velocity and sitting at different directions. And suppose we have n such particles. Okay. And the first question is how to describe such a system. I think we have already mentioned that we need to specify all the coordinates of those particles and all the velocities of those particles. And as a whole, it forms a huge vector, okay? So basically, we will have 3n coordinates because each particle will have x and y and z coordinate. And we also have 3n velocity components because we can have bx, vy, and bz components for the particles. So this big vector actually contains 6n variables, okay? So that's how we describe the particles in this big box. But we only describe the status of the particles, but we did not specify how it evolved as a function of time at this stage. Okay. So what Maxwell tried to convince people is that maybe in order to understand the behavior of this system with n particles, we can try to make the following assumptions. The first assumption he's trying to make is that suppose that these n particles are very dilute, which means that the density of particles is really low in this system, which means that those particles will not encounter each other very frequently. So colliding or interaction is very unlikely. So what that means is that suppose you have a particle I, and then it is described by this Ri of t and the Vi of t. And you have another particle J, which is described by Rj of t and Vj of t. Okay, so those two the coordinates that describe this particle I and particle J are basically to some extent decoupled. So these two are considered to be random variables, and they are statistically independent. Okay, so basically these two are okay. So that's a pretty reasonable assumption. So imagine that you have a big box, right? And you pick one particle at the left end and the other particle at the right end. Because it is really dilute, so it is very unlikely they will interact with each other. So at one side, the particle might doing something. It is basically very, independent about what the other side of the particle is doing. So that's a very reasonable assumption at the very beginning. Okay. And so this assumption actually corresponds to the previous figure that we just described, that this greenish region is basically the statistical independent assumption. Because at the very beginning, even though we have all the possible initial conditions, those initial conditions might not be independent. But now we are picking a very particular a very particular set of initial conditions that most of the or the particles are basically mutually independent with each other. Okay, and the idea to rational this assumption is that because we are in a dilute limit. Okay. So let me try to describe furthermore. So now suppose we take a little box in our system and we ask how many particles are there, and this finite element will have particle numbers that described by this density distribution function of position r and velocity v. and I'll need to integrate over this position r and possible velocity. So I think I'll stop here, and then later we'll say something more about or make more assumption about this density operator in the next lecture. And we'll take a 10 minutes break, and if you have questions, please ask me. Okay, see you in the next lecture. Okay, so hi everyone. I think we'll continue our lecture. So there's a typo. Thanks for the student who pointed that out. Actually, there's no temperature T. The entropy is just Kb nature log of the phase space volume. Okay, so that's the postulate given by Boltzmann, and we will discuss the meaning of that a bit later. But the key point is that the left-hand side is a macroscopic function, and the right-hand side, the information that we need is actually this accessible phase space volume, which is microscopic information. Okay, so let's continue our ideal gas example. So the first assumption that we made is that basically the coordinates and the velocity of the ith particle are independent of the coordinate and velocity of the jth particle. Okay, so that's the mutual independence assumption that we try to make at first. And this assumption is pretty reasonable because we are thinking about dilute system. And then next we are trying to describe the particle the particle number within a small virtual box, and we try to describe it by a density function f that is integrated over the space and the velocity of a little volume. Okay, so now we are going to include our second assumption. And the second assumption is that the position and the velocity of those particles are basically independent. Okay, and why it is so? In order to understand what's the meaning of that, maybe we can think in the opposite way. Under what situation the position and velocity will be dependent on each other? And that will basically happen when two particles collide or they are very nearby each other. Okay, because when the position is very close with each other, they interact, so their velocity needs to be changed. So how close they are will be definitely related to how they change their velocity. Okay, so the assumption that the position and velocity are independent is somehow related to the fact that we assume that they are non-interacting, or the event that they collide is basically very unlikely. So from that definition, the density distribution or the density profile can be factorized into the space part and the velocity part. Okay, that's our second assumption. And the third assumption that we are trying to make is that the density is uniform. And which is also quite reasonable because in this box, it's basically an empty box. So there's no reason that the density should be higher from one place to the other. So with this condition that the density is uniform, this function fr that we got previously should be written as n divided by the volume, which is the background constant density. Okay. And another thing or another assumption that we are going to make is about the isotropic property of the system, because now this particle, even though it lives inside the box, basically cannot feel what is happening at the boundary. So we assume that the velocity distribution can be factorized into 3 independent directions. So this assumption is also you can challenge that, saying that maybe at the boundary of the container it might not be true. But here we try to consider the case that the container is huge, and the ratio between the volume without container, without the boundary, and the volume that is close to the boundary is basically large. So this assumption is valid for most of the time. Okay. So that's the 4th assumption, and the last assumption is related to the fact that this distribution function should be just a function of the magnitude of the velocity. And this is also related to the isotropic symmetry of our system, because it pointing in one direction, or like moving in one direction with specific velocity, should be identical with the probability to move in another different direction, but with specific magnitude of your velocity. Okay, so that's the 5 postulates that Maxwell made at to analyze the ideal gas model. Okay, so we assume these 5 conditions at t equal to 0. But as we mentioned, if we start from this particular initial condition, those particles will start to collide with each other and do all other things. So it is not guaranteed that these conditions will always hold as a function of time. But as we mentioned in the previous case, that after you evolve for some time, because the system is basically a dilute system, we expect, or like we assume, that the chance that they interact is very small. So these events that these statistical assumptions are violated is very unlikely. Okay, so that's basically the spirit that behind all this assumption, and we are going to move from here to derive some information about the velocity distribution. Okay, so at this point, are there any questions? Yeah, dilute means the rho naught is small, but you should always ask small compared with what, right? Because rho naught has some dimension, like 1 particle per volume or things like that. So usually what we are comparing with is, let me try to draw a figure. Here is a big box. So maybe we have, particles moving, and this is the size of your container. And so when we are saying dilute, what we meant by that is that the average distance, maybe I should not use this. I'll just draw it as particles. Okay, so the average distance, let's call it something like a mean free path or something. And let's consider we have another container that basically have the same dimension. Basically the size of the container is the same. But when you lower the temperature, we know that particles will become, quantum mechanical to some extent. So you will see that there's a length scale which is related to your fluctuation, and that depends on your temperature. So when we say dilute, or the particle density is low, what we meant by that is that this LF is actually much larger than the thermal wavelength of your particle. Okay, so that's the limit where you will have ideal gas description to be a good approximation. So you can ask another question, like, what if this assumption is violated? So when this assumption is violated, what that means is that you have so many particles that is so close with each other So the wave function overlap becomes non-negligible. And that happens just nearby the situation where you need to take the quantumness of your system into consideration. And that could relate it to different kind of phenomena. For example, it could relate it to Bose-Einstein condensate, which is if your system is a bosonic system, we'll basically also discuss about that. And you can also have some fermionic Fermi gas. You'll see the Fermi gas phenomena, which means that those particles start to know each other, and they know the system is formed by a bunch of fermions. For example, it could be electron. Then if they know each other's are fermion, then they would need to follow the Pauli exclusive principle. Then you will see that they will accumulate at different position, and then not different position, at different quantum numbers, and you will form something like a Fermi surface, and then the behavior of that system will be very different with the classical system. So those are the situation where you need to take into the quantumness of your system into consideration. But now we are thinking about the other side, the dilute limit, which really means is that the mean free path of these particles is much larger than the thermal wavelength of your particle, so you don't need to worry about the quantum mechanics in this system. Okay, good. Are there other questions? Yes. Liouville theorem. We haven't talked about that, but yes, it should hold. And actually, it's one of the point why we want to use phase space as our definition to define entropy. It's related to the fact that phase space will be conserved. The volume of your phase space is basically invariant under the evolution of your microscopic components. But we'll discuss that later. Yeah, but yes, you will need to be satisfied in this simple example also. Okay, are there questions? If not, I'll just move on. So those are very good questions, especially when I say something is big or something is small. You should have a first question that you should pop in your mind is that small or large compare with what? Okay, that's a very important question in order to form some physical picture about the system. Okay, so now we can ask, following from this assumption, 1, 2, 3, 4, 5, what can we say about this function fv? Okay, so the claim is that if we follow the assumption 4 and assumption 5, we can get a conclusion that this fv as a function of the magnitude of the velocity should be proportional with something at this functional form. Okay, so this is something that we are going to at least convince you that it is very likely to be true. So let me try to write down the condition 4 again. So I think the condition 4 says, okay, this is condition 5, this is condition 4. Okay, so one question we can ask is like, what kind of function could satisfy this relation? And we can try to input this relation and see whether it helps us to understand that. So to some extent, if we start from this description, let me try to get the logic straight. If we start from this description, what that means is that, this fv of something should be related to some kind of exponential function. Okay, the reason is, like if you take natural log from both sides, wait. Okay, it should follow this relation if you consider the assumption 4. And in principle, we don't know what is this f of v, but we can make some bold guess, like, try to think from this side. And we should expect it to look like v to some power m, okay? Because we know, by the way, this is from the fact that of assumption 5, that we know that only the magnitude of the velocity plays the key role, okay? But if it is just the magnitude of our velocity, we don't know what is the dependence of this, the power of this function form. So if you use this as an input and try to put that into this relation, then roughly you'll see that the equation that you need to satisfy is something like this. Okay. And if you just look at this expression, just stare at it, then you probably can get the conclusion that this m must be equal to 2, because at the left-hand side, this absolute value of v is just square root of vx squared plus vy squared plus vz squared. Okay, if you take it to some power of m, most of the time, if it is greater than 2, then it will be much more complicated, and you will have cross terms. But the right-hand side, there's no cross term. So the easiest way to achieve that goal is that you just pick m to be 2, and then obviously you'll see it is satisfied. Okay. So this is more like a reverse check that from these assumptions, we should be able to anticipate that the velocity distribution should be some kind of Gaussian under those assumptions. Okay. So are there any questions so far? Okay. So if not, then we are going to use the normalization condition to figure out what is this f of v. So let's assume that this f of fx of v, let's just pick one direction, like in the x direction. Okay, it's some Gaussian wave function. Not wave function, sorry, some Gaussian distribution. Okay, and then we would like to interpret this thing as some kind of probability. Then if we want to interpret it as some kind of probability, then we need it to satisfy the normalization condition. Then we just try to carry out this integral. Okay, and then dx. Okay, and in our homework or slash lecture, we know this thing is just pi divided by square root of lambda. Then we immediately see that the normalization condition ax is just square root of lambda divided by pi. Okay. Then we know what this probability distribution function is if we try to interpret this thing as a probability distribution function. So now it is a piece of cake if we want to evaluate the bx squared. It's just the second moment of this discrete distribution function. And I'll just leave it as an exercise, and eventually you'll get the result. That's basically pi over lambda. Oh, wait, a bit I'm a bit confused. No. It should be 2 lambda. 1 over 2 lambda. Okay. So from this expression, we know what is the expectation value of the magnitude of the velocity square. It should be the Vx squared plus Vy squared plus Vz squared. Okay. And as we assume, I probably need to charge my laptop.